In section 1.3, we're going to be working on right angle trigonometry. And there are some specific things we can do when we're working with right triangles that we can't do necessarily when we're working with non-right triangles. So we're going to begin here understanding right triangle trigonometry, and in other sections we'll move on and discuss non-right triangles. So we want to be able to make sure that we can evaluate trigonometric functions of acute angles. That's what's unique about a right triangle. The other angles must be acute angles. And we'll use a calculator to evaluate trig functions. We're going to use the fundamental trig identities, and we're going to use trigonometric functions to model and solve real-life problems. So we're going to be looking at these 6 trig functions: sine, cosine, tangent, and their inverses, cosecant, secant, and cotangent. It's important when we start discussing some of these things that the relative position of the angle determines some specific things. So, for instance, we're going to be talking about the length of the side opposite, right? Opposite means it's on the opposite side of the triangle from the angle we're talking about, and also the side adjacent, which is the side next to the side we're talking about. Okay, so for this angle, this is the side opposite and this is the side adjacent. And we'll use the lengths of those in order to evaluate our trig functions. These are the identities that we would talk about. That's the sine is the opposite over hypotenuse. Cosine is the adjacent side divided by the hypotenuse. Tangent is the opposite side divided by the adjacent side. And then cosecant, secant, and cotangent are the inverses of the first 3. So remember, we're talking about the lengths of the sides in order to determine the trig functions of an angle. If we look at a problem like this one, we have a triangle here, and we're going to use these identities to find the 6 trig functions of this angle theta. So remembering, this would be the side opposite, it's 2. This is the side adjacent. They haven't told us what it is, but it's a right triangle. And because it's a right triangle, I know that the hypotenuse squared is equal to the sum of the squares of the 2 sides. So this would be 16 is equal to 4 plus b squared. So b squared will be equal to 12. So b will be equal to the square root of 12, or 2 root 3 when I simplify it. So this side has a length of 2 root 3. Now, if I want to work with finding these, I've got sine, which is opposite over hypotenuse. That's 2 over 4, or 1/2. And cosecant would be the inverse of that, which would be 2. So I have 1/2, and I have 2. Cosine would be adjacent over hypotenuse, so it would be 2 root 3 over 4, which would be root 3 over 2. And secant will be the inverse of that, which would be 2 over root 3. And then I'd have to rationalize my denominator. So I'll get 2 root 3 over 3. For tangent, it's going to be opposite over adjacent, so I'll have 2 over 2 root 3. The 2's will cancel. And then I'll have to rationalize the denominator. I'll get root 3 over 3. And for cotangent, I want the inverse, but I can go back to here to take the inverse, and I'll get root 3 over 1, which is just root 3. Okay, so by taking my right triangle, finding the lengths of all 3 sides, and then using them appropriately, I can find all 6 of these trig functions. So if we want to work with this, we've got a right triangle, we've got an isosceles right triangle. These angles are 45. And if I want to find the sine of 45 degrees, it's going to be equal to the side opposite over the hypotenuse. So that would be 1 over root 2. And when I rationalize the denominator, I'll have root 2 over 2. When I find the cosine of 45 degrees, that's going to be the side adjacent over the hypotenuse, but look at that, it's the exact same number, so that's also going to be root 2 over 2. And when I find tangent of 45 degrees, that's going to be 1 over 1, opposite over adjacent. 1 over 1 is just 1. Okay, if we move on and we start thinking about the angles 30 and 60, so we're going through and we're doing all of the common angles, multiples of 30 and multiples of 45. When we take a look at this particular triangle, we've got angle 30. If I want to find tangent of 30, so it will be opposite over adjacent. And we found that adjacent is root 3. So that's going to be 1 over root 3. And when I rationalize the denominator, I'll have root 3 over 3. And if I find the tangent of 60 degrees, that's going to be opposite over adjacent. It's going to be root 3 over 1. And that's equal to root 3. And you'll notice that the tangent of 30 had its inverse was the tangent of 60. So that means that the cotangent of 30 is equal to the tangent of 60. So that's dealing with supplementary angles. Here is a chart that's going to show you the values for sine, cosine, and tangent for the common angles, so 30, 60, 45. As we build out around the unit circle, these are what we build with, multiples of 30 and multiples of 45. And so you can look at this chart, and I personally would normally pull, rather than worrying about memorizing this chart, I would mostly think of being able to make the unit circle whenever I wanted to, so that I could then derive these values out of the unit circle. If I want to use a calculator to find the cosecant of this guy, okay, what we want to start thinking about is how do we convert the degrees, minutes and seconds back into degrees. So when you're working with degrees and minutes and seconds, you just want to think of the degrees as hours. So this is going to be 34 degrees plus 30 seconds over 60 seconds per degree plus minutes over 60 minutes in a degree, and 36 seconds over 3,600 seconds in a degree. So this becomes plus 0.5 plus 0.1, 0.01, excuse me. And what we have is 34.51 degrees. Now if I pull up my calculator and I want to find the cosecant, well, cosecant is the inverse of sine. You'll see that I don't have a cosecant key. So I'm going to find sine, 34.51 sine, and then find its inverse by using this 1 over x key. Your calculator might have an x to the negative 1 key. And I find that it's 1.765. Right, so this is how you would convert. Just think again like degrees are hours, 60 minutes in an hour, and 60 seconds in a minute, so 60 times 60, that's 3,600 seconds in an hour, okay, or in a degree. These are our fundamental trig identities, that sine is the inverse of cosecant, cosine is the inverse of secant, Tangent is the inverse of cotangent. We've talked about that quite a bit. Right? And this is all of these ratios written in the same manner. We also know that tangent is sine divided by cosine, and therefore cotangent is cosine divided by sine, because cotangent is the inverse of tangent. And then we have the Pythagorean identities, that sine squared of theta, meaning if I find sine of theta and I square it, which would be different than sine of theta squared would be squaring the angle measurement. So if I square the sine and the cosine of an angle and I add them to each other, it's going to equal 1. 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. So these are items that we're going to be working with as we move forward through this chapter. So if I want to apply trig identities, let's take a look at what we might do. So they're going to tell me what the cosine of an angle is, and then they want me, so they tell me that cosine is 0.25 or 1/4. They want me to find sine and tangent using these trig identities. Well, if I know cosine, that means I can find sine, because I know that sine squared theta plus cosine squared theta, in this case it would be 0.25, and I'm going to make it 1/4 because I'd rather work with the fraction, thank you, equals 1. That means that sine squared theta plus 1/16 equals 1. And so sine squared theta would equal 1 minus 1/16, which would be 15/16. And then if I want to find sine, I have to take the square root. So sine of theta would be equal to the square root of 15/16, which would be root 15/4. So that's that. And then if I want to find tangent, I know tangent is sine divided by cosine. So if I take root 15/4 divided by 1/4, that's going to be equal to root 15/4 times 4/1, because when we divide by a fraction, we invert and multiply. The 4's cancel, I get root 15/1, and that's just root 15. Okay, so in this case, the identities allowed me to take a small bit of information and apply it out to find more information. Here's another problem where they're telling me that tangent of b is equal to 2, and they want me to find cotangent of b and secant of b. Well, cotangent of b is easy. I know that the cotangent is 1 over the tangent. So for a, I know that the cotangent of beta is going to be equal to the inverse of 2, which would be 1/2. And then when we work on secant, I know that secant squared theta is 1 plus tangent squared theta. So I'll have 1 plus 2 squared is equal to secant squared. 2 squared is 4 plus 1 is 5 is equal to secant squared theta, and then I square root either side. Secant of theta will be equal to root 5. Okay, and that's, again, doing the same sort of idea. Now, I have picked these out already. These aren't supplied in the problem. But how would you find them? Well, you'd go back to this chart and you'd look at what's the one that's going to help me out the most. In this particular case, they gave me tangent and they wanted me to find cotangent. So if I go back here, I go, oh, well, if I know tangent, I can find cotangent by putting 1 over tangent. And then when you knew tangent, you wanted to find cosecant or secant, then you look at this identity and you go, oh, well, if I have this value of tangent, then I have only one variable, and that's secant, and I can find the solution. Okay, so use trig identities to transform the left side of the equation into the right side. So what they're asking me to do is change this appropriately until it becomes that. Well, I know that tangent, again we're going to go back here, I've got tangent and cosecant, and I know that tangent is sine over cosine, and I know that cosecant is 1 over sine. So those are both changes that I could make. So I can say that sine of theta over cosine of theta, that's tangent, is equal, or times, cosecant is 1 over sine of theta is equal to secant of theta. And I know that the sines will cancel and I get 1 over cosine theta equals secant of theta. And if we go back to those identities, look right here, secant is 1 over cosine. So now I can just say that secant of theta is equal to secant of theta. And this brings us to an odd sort of scenario around these problems, and something that may be difficult for you to get used to. It may not be. But if you take a look at this, they told me what to do. They told me to transform the left side of the equation until it became the right side. So we knew when we started the problem what the answer was. The item that we're looking for here in assessing this is, how did you get there? Okay, so these might be a little different than what you're used to. Again, right here we want to transform the left side until it becomes the right side. So when I look at this, cosecant theta plus 1, cosecant theta minus 1, cotangent squared, I'm not sure maybe what I ought to do. If I go back here and look, well, here's cosecant and here's cotangent, but this is like 1 plus cotangent squared, this is cosecant squared, but one thing for sure I know is that all of these have the trig value squared. So I'm going to go ahead and I'm going to go back and I'm going to multiply this out. So this is going to become cosecant squared theta minus 1. And I know that because these are conjugates, and a plus b times a minus b equals a squared minus b squared. That's what I've done. And that would be then equal to cotangent squared theta. Okay. So now let's go back and see what sort of progress we've made. Well, over here I have 1 plus cotangent squared is equal to cosecant squared. So I have 1 plus cotangent squared theta is equal to cosecant squared theta. And if I subtract 1 from either side, I'll get that cotangent squared theta is equal to cosecant squared theta minus 1. Well, this is cosecant squared theta minus 1, and it equals cotangent squared, so now I can just say that cotangent squared theta equals cotangent squared theta. Right? And I'm done. Okay, but it's the appropriate step by step to get to the two sides being the same that is the part that matters. So now if we want to look at another idea, we've got the idea of angle of elevation. So if I'm measuring from the ground and I'm looking up, it creates this angle. That's called the angle of elevation. And if I am perhaps above something, maybe I'm flying in a plane or something, and I look down, that creates the angle of depression. Just remember, it's always whether you're moving up or down from a horizontal location. So in this particular case, we want to figure out how tall this flagpole is. And we see we've got this horizontal line that's 19 feet. And then we've got this flagpole. And we want to know how tall is it. But we've got this angle of elevation. This angle here is 64.6. Okay, so when you think about what I might use, what I want is the side opposite, and what I have is the side adjacent. Well, opposite over adjacent, x over 19 feet, would be equal to the tangent of 64.6, right? Because tangent is opposite over adjacent. Now I want to solve for x, so if I multiply both sides by 19, I have 19 feet times the tangent of 64.6 will equal x. So if I pull out my calculator again, I can find 64.6 tangent and multiply it times 19, and I get 40.014 feet. 40.014 feet. So basically 40 feet. Okay, so again, we made a right triangle in order to solve a problem that is existing out in the real world. Okay, here's another one, but we're reviewing things from top down. Right? We know that we've got, this is 3 miles, this is a right angle, and this hypotenuse is 6 miles. And in this case, we want to find the angle. Ooh, okay. So I know that I have side adjacent and 6 is the hypotenuse. So adjacent over hypotenuse, that's cosine. So I know that the cosine of theta is equal to the adjacent over the hypotenuse, which would be 1/2. All right, so if cosine of theta is equal to 1/2, then what's theta? Well, I want to think about what angle would have a cosine of 1/2, and there's a couple ways I could do it. I'm going to go to the unit circle because I like the unit circle, and I'm only going to worry about the first quadrant, and I'm doing that because 1/2 from the unit circle would be the x-coordinate if it's the cosine. So 1/2. If you remember our 3 points that we use 1/2, square root of 2 over 2, and square root of 3 over 2. And I'm writing them 1/2, root 2 over 2, root 3 over 2. I'm writing them by which is from smallest to largest. And remembering that this one would be paired with that, this one would be paired with that, and this one would be paired with that as we travel around the circle. So my x-coordinate was 1/2. That's this angle here. So which angle lies at 1/2 root 3 over 2? And I know that that is 60 degrees. So I know that theta is equal to 60 degrees. Okay, I know that because this point was 30, and this point was 45, and this is 60, as I'm building the unit circle. Okay, so maybe we don't remember the unit circle. What else could I do? Well, I've got a key on my calculator that'll let me do that. So if I put in 0.5, and now I don't want cosine. Cosine allows me to tell the calculator the angle and have the calculator tell me what the cosine is. What I want to do is I want to use the inverse of cosine. That allows me to tell the calculator what the cosine is, and then the calculator will tell me what the angle is. And you see it's 59.999999999, which is 60 degrees. So I could have done it either way. So in this problem, I'd like to find the length C, right? This is the hypotenuse of my triangle, the length of a ramp, and also find the horizontal length. If we're looking at a ramp that's 11.5 degrees and it has to be 3.5 inches or 3.5 feet high, and these sort of incline levels are set by law to accommodate safety around people working in wheelchairs and things like that. So there are limits to how steep I can make this ramp. So in this case, let's say I've got a city code that says I can't make my ramp any steeper than 12 degrees. So to play it safe, I'm going to go 11.5. And I know I've got to go from level ground and I've got to go to a landing that's 3.5 feet. I want to know, A, as I start building my form, how far out from the base of this do I have to go? And C, I need to know what's the actual distance people are going to travel. So when you start thinking about this, I've got the side opposite. And what they want me to find is the hypotenuse and the side adjacent for 11.5 degrees. So I've got side opposite and I've got the angle. So what would be really easy for me to do at this point in time would be to say that the sine of 11.5 degrees would be equal to the side opposite, 3.5 feet, over the hypotenuse. Well, that was an easy one to write, but it's not necessarily fun to solve because my variable is in the denominator of a fraction, but I can handle that. If I multiply both sides by c, I'll get c times the sine of 11.5 degrees is equal to 3.5 feet. Okay, so it's not in the denominator anymore, but now I got to get rid of this sine of 11.5. If I divide both sides by that, now I've got a new equation solves for my variable, and this should allow me to very quickly get my answer. You'll notice I didn't bother to find what the sine of 11.5 was yet. I want to put it into an easy form to work with in my calculator first. And I know that I'm going to have 3.5, oops, let me write that correctly, 3.5 divided by 11.5, the sine of 11.5 is that. And so this is going to be 17 we'll call that 17.56. Okay, so this is 17.5, sorry, this is 17.56, my mistake. And now I have the hypotenuse. Okay, well that's nice. Now it's also very easy then to write another equation where I'm going to use the side adjacent and my newfound hypotenuse. So I know that the cosine of 11.5 would be equal to my side adjacent divided by 17.56. Now because I rounded this, maybe I wouldn't want to use that number. It's going to create a certain amount of rounding error. Equally, I could write another equation using the original supplied information of opposite over adjacent and do tangent of 11.5 degrees is equal to 3.5 over a. I could do either one of these, but I'm going to do them both because I want you to see how rounding error from my having rounded this value can affect your answers a little bit. So again, I'm going to multiply by a, I'm going to divide by tangent. A will be equal to 3.5 divided by tangent of 11.5 degrees. If I go back to my calculator, I'm going to do 3.5 divided by 11.5 tangent equals, and I've got 17.2. Okay, so A would be equal to 17.2. That's the one I'm going to go with, 17.2. And I'm doing that because I have more confidence in that value. I have more confidence because I didn't round the 3.5. But let's solve this one. If I multiply both sides of the equation by 17.56 times the cosine of 11.5 degrees, that will equal A. So over here I'm going to find 11.5, I'm going to find the cosine. I'm going to multiply it times 17.56, and I'm going to get 17.2. I actually got, this would be 17.21 if I rounded it correctly. But you can see I essentially got the same value. Okay, it doesn't really make any difference which one you do. You should be able to drive through and get your answer. Just know that you want to minimize rounding error as much as you can. So if you can avoid it, you should. So what we've gone through the right angle definitions of the trig functions. We've described how to use a calculator to evaluate trig functions. We've used evaluating the trig functions of acute angles. And we used a calculator to evaluate trig functions. We've gone through the trig identities and we've solved some trig identities. And we've gone through how to use trig functions to model and solve real life problems. And that wraps up for you section 1.3.